So there's an analog input to a DSP system is digitized with 16-bit ADC. All right, so the peak-to-peak amplitude is 10 volts and lies in the band of 0 to 10 kHz. So the highest frequency of interest is 10 kHz. So calculate the required stop band attenuation required by the anti-aliasing filter. All right, so the anti-aliasing filter want to cut off the unwanted signal, right? So we want to cut out those signals. So after this filter, because this is not ideal, is not a zero, is still something left. It's still something left, okay? But we wanted this one is so small that this ADC won't pick it up, okay? What does that mean is the quantization error, okay, should be larger than this this signal after it's been filtered. All right, so your attenuation rate should be this amount. Okay, so you're gonna reduce your input voltage to less than this value, so ADC won't pick up. That means you totally filtered it out. Okay, so for this case, because B is 16 and the A or 2A peak to peak is 10 volts, is actually exactly the same as the question 3. So if you refer to question 3, you will find the attenuation rate, which is a signal to noise ratio. So it's a minimum. The minimum attenuation is actually 20 log 10, 1.5 root square to B. Put it inside, and that was 98.095. Okay, dB. Sorry, this is a unit in dB form. All right. So part B is the sampling frequency to keep the aliasing error in the passing band to just below the quantization error, the level. Okay, so this is similar to the one we just did in question 4, but this time we are using a 6th order but worse. The previous one is a 3rd order. So for this one, we can have draw the, okay, so again we wanted this frequency. There will be a overlap because this will be a capital Fs, okay, the sampling frequency. There will be overlap, but we wanted this, this is cutoff frequency, Fc. We wanted this one be so small that it cannot be picked up. Before, if you remember how we calculated attenuation rate, it was 2% of the passing band, okay? But for this one, we giving a new number here, okay? Making a new number. So this one, we need to attenuate it from bottom, from top to bottom. So we got a 98.1 dB. That's the given. So we're gonna use to solve this question. So again, for this one, we gave this one a name called FA, and if you count from here to here is FA again. Okay, so Fs equals to Fc plus Fa. All right, So the FA, we need to figure out how much is FA. We're gonna use this attenuation. So we start from the Butterworth filter. This time is 6 order. So the magnitude of this filter at a particular point, frequency, which here we want to know the magnitude. So there's an equation for that is 1 over 1 plus FA over FC. This time is the 6th order, so here is a 12 to the order of 12, and we do a 0.5 order of 0.5 outside of that. So this one is HFA magnitude over a signal, because this is the noise. Okay, it's actually the noise over signal, and the signal here we're using is 1. So this one is 1. Okay, we don't know noise to signal ratio, but we do know signal to noise ratio. Okay, signal to noise ratio is equal to, this one equal to 98.1 dB. Okay, and so this one just 1 over H FA. Okay, so 1 over HFA. In terms of this one, let me move up a little bit. So in terms of this one, we got 1 plus FA over FC to the order of 12, and there is 0.5. That's just 1 over this one. Okay, so this part, okay, is equal to this part. All right, so what we need to do is we giving a 20 log base 10, so make it a dB. So this one just equal to 0.1. So both sides are dB now. Okay, and if we solve this equation, we will find FA over FC equals to 0.55. Okay, so FA equal to FC multiply with 6.55. So FS gonna equals to 7.55 FC, right? Because FS equals to FS FC plus FA. Okay, and how much is FC, the cutoff frequency? So if you remember, the signal of interest is from 0 to 10 kHz. So we're gonna use the high band. So the FC will be 10 kHz. Then the FS just equal to 75.5 kHz. Okay, so if you have this sampling frequency, that the error can be made sure is small enough so the ADC won't pick it up. Okay, of course, if you have a higher frequency than that, it will even better, but that will be the minimum for you to not picking up this noise. Right, so that's this one.